All right, welcome back, everyone. Let's get started. Yeah. Should we get started? All right. Yeah, welcome back. This is basically the last real chapter for our whole course. So I'll come also back to some of the administrative questions a bit more later on. I think there were already some questions, and exam and other stuff like that is probably on many people's minds already. So that's also talk for today. But before coming to that, basically, I want to wrap up some of the earlier simulation-based topics that we had over the course of the last several months by now, basically. And so that's also a bit of a switch from what René talked about in the past 2 lectures. And that's also why I'm taking over now. In a way, that's a good cut in terms of topics. So I want to come back to, really kind of wrap up topic that is actually or could potentially apply to fluid simulations as well, what René talked about basically. But I'll actually explain it in terms of rigid body simulations that we talked way back in October by now. But yeah, this is in a way a topic that just targets coupling different kind of simulators. So it's potentially interesting for some of it is interesting for other types of simulations. And the last real subsection, this cross simulation algorithm, is actually targeting that. But yeah, first I want to go towards a bit of a engine viewpoint. So I mentioned this book by Millington in the beginning already. So one way to see many of the materials here is actually going towards a physics engine. And we've mostly looked at relatively relatively specialized simulation algorithms. And now we want to come back and look at this with a bit more distance, which unfortunately also makes it necessary to go into some of the details to fix up aspects of the algorithms, as you see in a moment. But yeah, for this engine viewpoint, there's a graphical overview that I want to follow, and those are the 4 steps shown here, which you'll also find on some of the slides in the beginning, especially in the corner as orientation. So we have integration topics. That's in a way a bit related to the core simulation that we talked about, collision detection. Details on what's meant by that will follow in a moment. Resolving penetrations, and then resolving velocity problems, if you want. And these 4 main topics you'll see at the top, so that you know basically you're moving along this process of what a typical engine would undergo in each of the update steps in the following. Yeah, so the first block, as mentioned before, is this integration part. So that's, in a way, easy. That is collecting forces and then integrating them over time, which follows our main simulation algorithm for rigid bodies that I had on the slides a couple of times back then. I don't need to go through, I'm sure. So all the main steps, computing Euler steps to integrate all the linear and angular components of our body representations. Yeah, so potentially for real applications, also this force collection that's just summarized with 1 line here could, of course, be quite involve all kinds of external forces or user input or so. But that's application specific, so I can't really talk about what is necessary here in a general way. But typically, as I'm sure you all know by now, forces can be added up, they can be accumulated very easily. So in a way, that is more a question of handling that in a way that's appropriate for some application. All right, now we have the forces. We made our step. As I'm sure you all also remember is, well, we kind of, with this simulation algorithm, what we in a way doing is we are doing these steps blindly, We're collecting the forces, and then we kind of shooting our objects forward in terms of motion or in terms of their orientation. without really taking into account the whole world or the scene around them. So typically, that's where the errors occur, right? If we would know over the course of a time step, my object, maybe the sphere, right, is colliding with the table, right? I could directly fix this, but if I'm just making a small step, my bottle might go from here to the other side of the wall, right? And then, or actually somewhere into the wall, which I can't demonstrate in reality that easily, but I'm sure you know if you tried the exercise what I mean here. So next step is this whole collision handling. And one key component here is, which René explained, is updating the acceleration data structures, geometry, these geometric aspects of the simulation typically go into the collision step. If you have many objects, right, this quadratic scaling, if you do not have an acceleration data structure, would quickly kill the performance. So that's crucial to get large, complex scenes realized. What was also briefly mentioned, what's in practice often quite useful is if we have something like a static scene, right? Most of this room you could probably treat as static if we want a scene to take place here. Right, so this table obviously moves fairly easily. This might be different every time, but right, most of these fixed chairs here we could probably pre-compute, get a very good acceleration data structure that handles collisions with those. And that could just be loaded if we want some simulation to take place in a room like this one. With those, we can generate data for the contacts, for the potentially colliding locations in our scene. And this is now the output of this collision detection step, basically a list of this pairwise intersection that we find. It's typically quite local to geometry, right? So on a vertex or triangle level. So one step often is, in practice, to reduce this somewhat. If for a single object, right, you find 1,000 points, that's typically not so useful for the actual simulation algorithm. In a way, the most salient, the most crucial points, say on the outside of a face, could be the most critical ones. Or in some cases, you can imagine, right, mapping this onto corner points of a face. Yeah, I do have a small scene here. So essentially, nonetheless, what we get out here is ideally a reduced set of collision points with the corresponding pairs that we can then treat in our impulse handling. And one way to realize this reduction part here is actually to limit the detection to single collision pairs. So the idea here is that we treat the most severe, typically geometrically, that's measured in terms of the distance that we enter the other object, collisions one by one, and accumulate this over the time steps. So assuming that we have relatively small time steps, right, we might not have to resolve something like a whole face of an object in one go, but if we treat the approximation approach here, the worst ones in every time step, and we have enough of the time steps so things don't go out of hand, we can actually, over the time of several time steps, get all the important points to also cover a larger area. So, right, for the first step, that's obvious. If we don't have colliding ones, we take the very worst one in the first step and then check the current ones that we have. First step's just potentially 1 or 0, but we check the relative velocity of the ones that we have. We classify. If it's too small, right, it could be actually a resting point. If it's going out, the objects detach. It's solved, but if they keep on going into each other, it's a contact that we need to keep. But based on the current one we have, we have to compute the next bad one that we can find from the current configuration, and then add this to a list, typically one with a limited size. Before, we don't want 1,000 points, but we want at least 3 to make up a plane, or maybe a slightly larger set of collision points that cover representatively the faces and the areas of different objects that touch. Right, but as you keep on accumulating, potentially also removing some that either get resolved or are less severe than others. So quite a few heuristics go into this, but the main idea is that we keep on building up a list of collision points to cover larger regions over the course of several time steps. Because if you think about the alternative, doing this in a single step would actually require some kind of clustering or detection of geometry in the collision points, which is potentially a bit tricky. A next important step is to actually resolve the things that went bad geometrically in the time steps. So now we have some colliding points, but as mentioned before, like my bottle might be inside the table, which is not so physical. So a similar thing happens with velocities. I'll come back to that in a moment. And they're typically coupled, as we also briefly mentioned, for resolving collisions with our impulse handling. But in practice, we can actually treat them separately, again, to avoid solving larger complex systems of equations in single time steps. Yeah, so the idea is that, a bit similar to the previous approach, I think this will come back, that we treat relatively localized interactions on a per time step basis and keep on doing this repeatedly. So replacing larger monolithic solves with smaller updates that happen over the course of several time steps. And I will have some more examples of that in a moment. So this is actually the slides we already had a couple of weeks back, actually, right before the collision detection chapter and the PDEs. So the idea is to reuse this impulse-based formulation to update the position and orientation of a rigid body that we have. The motivation for that was that the impulse handling already kind of nicely redistributes the effect of a collision onto the different components that play a role in, say, a rigid body simulation, right? The masses specifically, and for a collision, even with 2 bodies only, we already have 4 of those, right? We have the linear and the angular mass distributions, the inertia tensor, for both of our bodies, and the impulse in a way nicely, right, weighs an update based on these 4 quantities. So if there's a body that, for example, starts spinning very easily, the impulse gives us, right, an update of the orientation for that body and, say, displaces the center of mass less strongly. So in a way, this is a natural point to use here. And right, I don't want to put up the equations again, right? They're a bit bulky or large, but I hope you have it in mind, this redistribution with the different terms. And this is also what comes into play here for resolving these unphysical positions. And theoretically, if we would just from one object change any of the quantities, well, either the position or the orientation, that changes the geometry of a scene, right? So unfortunately, theoretically, if we would make any one update to one body, we'd need to basically recompute our data structures for collisions, because just by changing, say, center of mass or our orientation slightly, we typically don't now know what might have happened we might, or we should actually run it through our data structure to see which other objects it collided with, and potentially we would also need to update our data structure to take into account this new position of our body. But because the geometries typically are complicated for these simulations, that's usually impractical, right? And this is just one object. We might have to do this if we would want to be really correct many times in a single time step, so that very quickly becomes impractical. And hence, one approximation, again, that resolves things over the course of several time steps, is to actually keep the contacts that we collected before. So we're computing contacts, we're not updating them. We just update these point-wise information that we have from the updated bodies. So we keep this accumulated list of collision points. We potentially do change, well, in this case, the position and orientation, so the location of a rigid body, and update the corresponding quantities. So with the potentially the position of the collision point, in this case, how far the bodies are inside of each other. It's kept a bit more generic here, so before we come back to this for velocities, and then also the actual velocity might change. But so what's not happening, what's important is, we're basically not deleting or computing new collision points, but we're keeping the set that we have from the previous step. Yeah, here's a simple example without equations, just to illustrate the concept here a bit. This does not fix things globally, just to make it also clear on a picture. So if we have even a simple object with 2 points colliding here, if we go in point by point, we can actually start fixing just at the right vertex, pushing it up. So on first sight, now this point is correct, but now this one is still wrong, right? Even if we just collected this one time step, we know both were wrong. We fix the first one. Now we go back to the second one and fix it. Applying the impulse will give us an update of center of mass and orientation, and probably push our object a bit up, but also rotate it back to the left. And now we're back to, a state that's not so similar to the first one, and the right point is now actually again deeper inside and not physical anymore. If you do this in the right way, potentially you can iterate on this, and at some point this object will kind of jitter out of the other one and be fixed. But this basically relies on this happening over the course of several time steps. So what I would not recommend doing is to try and fix this in one step. This is actually potentially an involved process here. It's very clear visually and obvious, but in the general case, and we'll come to some pretty bad ones later on, it's actually tricky to find out what exactly the geometric configuration of these contact points is and in which direction to go to resolve it. This is, in the general case, a very difficult problem. Yeah, and also what's typically not happening is if we have a case like this one where we only find, say, one edge of the box colliding, and we apply a similar resolving update, suddenly in this example, right side could start a collision with the floor, but this in the proposed algorithm actually would not be detected until the next time step, because in one time step, we just have the set that's coming from the collision step. We're not updating the collision points. So this right point in the current time step would actually not be updated or not be taken into account. Yeah, because this is this iterative process of doing many small updates, potentially it might be required to do a lot of them, or because they also the updates tend to be smaller, this might be almost a never-ending process. You might need millions to really resolve this in one time step. So what's typically done is to use a limit, to have some kind of computational budgets and say, well, we're doing 100 updates, and then we just move to the next time step. Seems like a good fix. At least then we can guarantee a certain update rate or a certain computational load per time step. But what could happen then, what in practice is quite bad, is that there might be a few really bad large collisions. Right? You might have some large heavy object that's crashing into wall, that's updated, or that's really taking all of these 100 update iterations, and then we have a few small ones, I don't know, some smaller, a light piece of cloth around a character, and all the resources are spent on the big heavy ball, and a piece of cloth is not touched at all, which means it would just go through our character, not properly be handled with the collisions, which would be very bad visually, even if its impact in terms of mass for a scene might not be so crucial. But so the one way to address this is to make sure that we have a heuristic approach. Basically, we at least one pass over all of the objects, make sure every object that had a collision is touched at least once. And then afterwards, we actually start fixing up the worst ones, potentially the really heavy objects that could damage the behavior in the long run. But this way, it's a bit of a compromise that also lighter objects and all of the ones that we have colliding in the scene are updated at least to some extent. Yeah, the alternative, really iterating until we make sure that all of the collisions are resolved, can be really slow in practice, and it's also hard to know how long this would take. So for real-time applications, this can actually be a bit dangerous if you want to guarantee a frequent update. Yeah, and then also one of the requirements here that we also touched on back in October was typically one aspect to take into account for visual applications at least is that the angular motions should be updated a bit less, because those can lead to very obvious and unappealing jumps in the orientation. So typically more weight is put onto the center of mass updates. Right, but this represents in a way, typical compromise that you find in these engines in terms of computational resources that we have and the speed of the resulting application. Some more comments about the velocities. So as much as from these fixed Euler steps our positions and the actual geometry can go wrong, right? The velocities can go wrong in just the same way. So you can imagine all of these previous pictures just looking at the velocities of the points. And we also want from the collision resolving step that the velocities actually go out of each other, right? We don't want these unphysical ones that never would happen in reality, that objects keep on being interlocked and moving into the volume of the other material. So computing these relative velocities at the collision points is likewise a step that can be treated in much the same way as just described for the actual positions of the points. Now the picture slightly changes, but in contrast to this geometric penetration depth, as it's often called, like how far the objects are inside of each other, now we actually need to look at the relative velocities. And because, framework, those are defined to be negative when the objects go into each other, we're actually now looking for the smallest one, meaning the one with the largest negative component going into the other object. That's potentially the worst collision, because there we have the largest velocity going into the other object. Right. If we make any update there, a bit similar to the geometry, right? If we have an object, all of the vertices change, and in a similar way, also because for rigid bodies, all of the geometry is coupled, it's moving together. If we change any part of the velocity, the linear one, potentially even worse, the angular one, which might change quite a bit of the behavior of the outer vertices. All of the points involved for colliding bodies need to be re-evaluated. Right, so if any one of the changed bodies is colliding with others, then all of the corresponding collision entries need to be updated, because potentially, well, at least those are the points we found. For all of these, we need to check how the new velocities influence the relative velocities at all of these locations. And then, right, the updates are again computed with our impulse equation from before. Does that make sense? All right. So one parameter that typically comes into play here is also tolerance parameter. Also something we'd actually cover quite a few times. In these real-world engines, you typically have quite a few tolerance factors, epsilons they're typically called, right? Some margins that tell you this is essentially 0 or this is still fine. And these margins typically also depend on your actual application. You have those in engineering applications as well, by the way. So practice any numerical application actually needs those kinds of ranges. So it's unfortunately something that you cannot really get around. So in practice, one point here is that, for example, for collisions, it might be beneficial to actually give it a certain margin. So we could say that only if objects are into each other by a certain amount, larger than this epsilon, we really treat it as a collision. The same holds for the velocity. So the motivation here is a bit that if things are so small that they're on the scale of this epsilon, it could actually potentially be a numerical artifact, that the computation really was off by a small amount and it really was not a collision, or at least it's a collision that in the current application is actually not really visible. And then, we could argue, well, we actually don't need to treat this. And then we can skip a few of these collision points, handle all the downstream processing and checkups in the resolving process. So if we can reduce the number of collisions found, we're sure this is not bad, then this potentially saves quite some work in the algorithm. One other thing that's nicely visualized that might be clear, that I think it's worth putting it on the slide explicitly, is the data flow in this pipeline. So we have our rigid body data, the main objects, with all the center of mass, linear, angular components, and the associated geometry. And for all this collecting of forces, right, that's typically just an accumulator. So potentially that is one vector 3 per object. Well, angular and linear, but this is quite easy and just typically updated in the process. Likewise, the time integration step updates position and orientation and linear and angular velocity, but this is calculation, and then we have the new values in our rigid bodies. What's a bit more interesting is this contact generation process that really generates a new data structure, right? That's this list of contact points. And this one, as mentioned before, potentially persists over multiple time steps. That is something that's built up and accumulated. So in a way, this is pretty central to the whole algorithm. And this goes into the contact resolution. Again, the contact resolution does actually not change any of these points. Might reclassify, but just works with the contacts and the rigid body information to resolve the unphysical states. But that's a bit the data flow for these different steps of the simulation. Yeah. This all scales in terms of the complexity of the algorithms with the geometry and the number of points that need to be treated, and also with the number of objects. So what's actually typically quite tricky are these situations that I also showed in the preview movies last year, with these many blocks, these wooden blocks, very simple objects. So in terms of geometry, this is actually not too difficult, but just the sheer mass of these objects, and also the height of, potentially there are quite a few objects in this pile of blocks here that need to be treated. And to make this stable, we actually need to detect that across this whole height here, all of these objects are resting, but not, don't need to repulse or shift around the others, but just rest on each other. Then, what's also a factor here, we're actually working with these lists of contact points. So if these would get too large, a step that happens quite a bit is finding the next to handle. It's basically a priority queue. So also some care should be taken in terms of underlying algorithms, how to implement this priority queue. But this is in a way a standard problem in computer science, but something to be aware of here. Yeah, there are two more points that I want to mention in the following that relate to practical rigid body engines, and that's sleeping and precision. 1 second. So these sleep states are actually a very important thing for many simulations. And the idea here is a bit similar to what you would encounter in rendering. So for rendering, it's obvious, rendering a certain scene, right? We don't want to spend a lot of effort on stuff that's not visible, right? If I'm interested in this view of the room, I don't want to spend a lot of work with things that are behind me. So for simulations, it's unfortunately not that simple, because objects that I don't see obviously need to move, right? If I throw a ball in the air and I'm not looking, I still want it to fall down. Not that the next time I look, it starts coming out of the air, but obviously, in a way, we have to treat all of the objects in the scene. But here's objects that don't move, that are basically static. Those we want to spend as little time as possible on. But yeah, invisible objects we definitely still need to treat. So we can't do it in the same way as rendering. Now, in a way, it's not too complicated. We need to detect when our objects are moving, and then we can make them sleep. We also need to check when can we actually wake them up. And if you think about it from a simulation perspective, the most meaningful in terms of physics would actually be to look at the kinetic energy, to be specifically of the object. I think we had this briefly on the slide. Energy is mass times velocity squared. We have both of our kinds of motion here, the linear and the angular parts. So we need to look at mass times linear velocity, or center of mass velocity squared, plus inertia tensor times angular velocity squared. That would be the kinetic energy of a body. And if that's small enough, right, it really would make sense to say this object is not moving at all. In practice, similar to the impulses actually, these mass terms can make this a bit difficult to handle. So if you're not too interested in displaying this would be a good approach. But for visual, for game-like applications, typically even a light object, a very light styrofoam box or so, it still might be very obvious if it's moving or not. So what's easier to handle is actually not take this mass weighting into account, but just look at the velocity magnitude. It's a bit less physical, but as you can see, it's closely related. Just removes the mass scaling. And this is often easier to find thresholds for in practice. With that, we can detect if it's small enough that an object should sleep. Of course, these objects still need to go into the collision detection. We need to still check a collision. Even if an object is resting on the floor, it can, of course, still collide with some other objects. Now, there's another interesting component here, that is stability. It's essentially a classification problem, right? We have an object, we want to know, should this be sleeping or active? And we want to classify these two states. We need to stabilize this, because in practice, our signal will probably look a bit like the green one. This is stock market, but the simulations nonetheless can look similarly. So it's often not a very smooth line, right? There might be jumps, it might jump up and down. And to stabilize this, what's actually pretty often done is known as the complicated name exponential moving average, but it's super simple in practice, and probably because of that also widely used. We weight the current value, that's our VT, or right, we compute a current estimate based on the current value at time step t, plus some history, in this case called V tilde, and we basically weighted the previous and the new one by a factor of beta. In this case, right, for now ignore the h, just by some factor beta, and it's a linear interpolation, right? So we have beta times the old plus 1 minus beta times the new one. So imagine, right, if this factor is actually 0, it's none of the old one, it's always just the new one, that would be no smoothing. If it's, well, 1 wouldn't make sense, it would never update, but it's very close to 1, then we're essentially mostly keeping the old one. The new value has barely any influence. So this weights, or essentially gives us the weight for the previous, for the history component. So if you take this to be large or close to 1, it basically puts a lot of weight onto the history of the values. Now, you can see here there's, in the equation, it's written as beta to the h with an exponent, and that comes if you want to take a certain time step. So if you want this to be actually valid for a step t plus h, then for this factor to work across different sizes of this h, we actually need to weight this by, or take an exponent of h into account for this factor, such that it also works for different time steps. But this really only plays a role if you want to change this size of your update step. If you apply this, this gives you this nice yellow line here, which removes a lot of the noise in the actual signal. And right, as you, I think it's pretty obvious here, this yellow line is now much easier to look at or to set a threshold for than for the green one. Nonetheless, this is actually not enough to make it really stable. What's used in practice as well is right, another component. The same, of course, also holds for waking up, right? So we have an object based on the threshold that can be put to sleep, but we also need to reactivate it, and that's the same process. So here, unfortunately, it's not enough to just look at the current velocity, because it could happen that, right, we have some sleeping objects, and then based on our collision handling, a new object comes along. So from some collision here, this object might receive some forces, and we actually need to take into account what kind of forces would be added from collision detection, and then the impulses that we compute, such that a sleeping object can actually go over the threshold and start moving around again. But nonetheless, it's similar. It can be based on the same velocity, magnitude, quantity that we looked at before. Right, and potentially, in our setting, this would over several time steps, then could wake up a whole chain of other objects. But yeah, so what's in practice actually interesting and important for this classification is what's often called hysteresis. So very interesting, it comes from worn out rubber bands, so it's a kind of memory effect that materials also show in reality, because the deformations they experience really change the structure of the materials. It's kind of like a weakened response. And the idea is, if we now look at our energy or magnitude value, here it's in terms of energy, but you can replace it or imagine this being the magnitude, of course. If we now set a certain threshold and say, yeah, based on a 10 to the minus 4, if it's above awake, below the object sleeping. If we have some object that behaves like maybe this, of course, a bit of a worst case, but if you simulate enough of these objects, especially a large pile, this is pretty much guaranteed to happen. This object obviously and unfortunately would now change from active to sleeping several times back and forth. Although looking at this, you'll probably say, well, this looked like it's not participating much, right? It's going towards being not active. But in this scenario, it would actually wake up in between 2 times because just slightly goes over the threshold. So with hysteresis, the main idea is that we separate these thresholds. So instead of just having a single value above below, we say the one state is actually achieved if we go below one threshold, and then we don't change it back when we go over, but we only change it back once we go over a higher one. So here we actually need to go over the threshold much further, and only here in this region we change the state back to being active. So that's what's often known as hysteresis. So for this to specify, right, you need more than one value. It needs more tuning, unfortunately, but you can often say, well, we might have chosen a single one here in the middle, and then you say, right, there's this kind of band that you define with plus and minus around it. That would be one way to specify this. Right, in this example, it's chosen like this. Now we actually get a nice behavior that the object is awake, and then here, once it crosses the sleeping threshold, is deactivated and does not wake up anymore in the rest of it. So this prevents this jitter of states. And yeah, potentially also saves resources because all this waking up, going back, of course, also needs some computational time, typically in practice. But I think both of these is exponential moving average for smoothing the time series, and then stable threshold with hysteresis is a pretty common concept, actually. Yeah, another interesting, unfortunately challenging topic in these simulations that was also mentioned a bit before, that's worth mentioning here again, is floating point accuracy. I mean, we do have guaranteed results. Normally you would think, right, this is an ancient problem solved by now. But for example, just multiprocessing, GPUs with multiprocessors, like GPUs, completely messes up because of the execution order. So as soon as you can add up different values in a different order, it's not guaranteed, results can be very different. That being said, here directly some guidelines. I would recommend around 10 to minus 5 for single precision. Double precision is quite a bit more accurate, but if you look it up, both of these would be accurate on paper to much higher, much smaller values, but I would recommend to stay away from those quite a bit to get stable results. And right, I think, well, this sounds artificial. Probably wouldn't need to bother, but you can interestingly, if you look online, show the effects of this very clearly with very simple programs. So here's a super simple program that implements an odometer, so it should basically compute how far we've gone with a car or so. And if you look at this, it's a full program. Please, you can find it online, but you can try this small C program. We're basically counting the distance, meters, and then we're making here, this is 100 million iterations. And now we are just incrementing our counter, the distance that we've covered, by every time 0.01 meters. And now we're making 100 million of these steps, right? We are adding 0.01, so we'd be expected to cover 1 million meters after all of these iterations. And then interestingly, if you run this, right, you're not getting 1 million, but many compilers actually, all right, this should be guaranteed. This should actually be for all compilers, because this is not even taking into account the effects of different threads, but really just floating point accuracy should give you basically 262. So why is that? Well, the problem is that floating point precision is relative to the value we have, right? So if we're only adding up many numbers on a certain scale, then this might work nicely. But as soon as these numbers accumulate and the main number, in this case the meters, moves to a different region that's far enough away from it, then the changes are truncated. And this is a worst case example, because we're always just dealing with the same change. So if we somehow at some point hit a value where this is not taken into account anymore, it's just completely ignored. I could make billions of iterations. This change would not be seen in a certain floating point representation. This is obviously a very bad example, but it's really just in addition, and you can imagine the same could easily happen in multi-threading. So the danger is, in multi-threading, we could have several small values that added up would be large enough to contribute. But if for some reason a big number is added first, all of these small numbers that are added later on will not be seen. So unfortunately, also with multiple threads, if we are out of luck and we first get a big number on an accumulator, then all the smaller ones are actually not seen anymore and might not show up. So unfortunately, for multiple threads, this is a problem that can also quite easily happen. Yes, there's a question. There should really be 262. 0.01, yeah. It's always adding a very small step. Exactly. So in the floating point representation always has lower accuracy, actual number, than an exponent, right? So if you map certain values, and especially into this this representation of this number, it will basically give you 0 and not change at all the current the current number of this value. So it's from a website. We can post the link later on. Please give it a try. But yeah, this is really a problem with floating point representations. This problem with multi-threading is a bit more difficult to show, and unfortunately also non-deterministic, right? So the order of different threads in your program in which it's executed is typically, it depends on system load or an update that's running in the background, so it's often difficult to reproduce. But you can imagine that this block here could be something that's basically running across different threads and just adds onto some, even if this is synchronized, onto some counter in an unknown or not guaranteed order. As soon as you have such a part in your program, you typically need to be careful. Then things could get lost. A fix to make it deterministic, to at least get guaranteed results that would not even fix this, is to have if you run this with multiple threads, to have a guaranteed order how it's added. Then you always will get the same answer, but you might still run into similar problems. In practice, you could, of course, also fix such a problem by changing the accuracy of just this accumulator. So typically, even if all the other quantities, I'd imagine this is a force that's computed somewhere externally, this we could keep a single point floating point accuracy, but a force accumulator, if we know this is important, the accumulator itself could be made for the accumulation, higher precision, and then afterwards, once we're done accumulating, we could actually map it back to a float in our rigid body accumulator or so. The problem is really just this adding up of multiple values into this temporary state. So yeah, main takeaway message here is if you have situations, I think this at least think about what data types you might use for these accumulator variables. And yeah, this similar problems can actually also interestingly come in other scenarios. Level, layout, or the units of a world are an interesting scenario where if you don't think about it, this can give weird results. If you try to do physical units for some world that you have, and yeah, your origin is in a certain part of your scene, and your scene is large, if this is on the scale of, again, maybe kilometers, and you're saving meters, then you have millions or several orders of magnitude in your floating point representations. And then, unfortunately, if your physics happen here, or offset by a few million meters, might suddenly give very different results. Although we know, the physics, the ball falling down, should be exactly the same everywhere in our scene. But just because over here we might not be able to compute very small steps and might run into these runoff problems, suddenly things go wrong. So this is problematic. In practice, what you can do is, what's often a better idea is to use more localized coordinate systems. So it's really a question of picking a good coordinate system. And for example, zones or dynamic coordinate systems can alleviate that. But yeah, taking large scenarios or trying to deal with our solar system in one single coordinate system around the sun, will give you problems if you go towards Pluto and so on. And mostly something to be aware of. Yeah, double precision itself is of course attractive, and could be handled nicely, but it's not something I would recommend, because in the end, it actually just requires twice the amount of memory, and also many CPUs are not that fast doing floating point, double precision floating point operations. And the other ones, like these zones or adaptive coordinate systems, are unfortunately a bit more difficult for the implementation, but nonetheless, probably a good idea. Yeah, so as a small in-between summary, if you implement all of these, you can actually get quite stable rigid body simulations. Also, if you take into account these extensions that we discussed, things like quantitative friction and stable build-up of collisions and stacking, it can be expensive with these iterations over time. and you still can actually in certain situations get things like jittering objects and some sliding artifacts, but I would say it's actually still a fairly decent overall quality of rigid body simulations that you can get out of a simulator with all of these extensions. She does follow quite closely the Millington book here, but in practice, this is just a selection of certain extensions that are relatively easy to implement. If you look at current other engines, you might actually find quite a variety of different and also potentially more advanced ones that are often used. Yeah, I think that's actually a good time for a break. I do want to come back to a different type of simulation algorithm in a moment, but let's do that after a 5-minute break. So feel free to stretch your legs. All right, let's continue. Great. So there were some questions about the exercise exams. I'll come back to that in a moment also. We can discuss also points that might be relevant for more than one person in the following. Before coming to that, I want to show one different simulation approach, a bit more roughly, because this goes into a bit more complex algorithms, partially that we have not all covered, but more to show what could differ. So we've talked about this relatively basic setup for the rigid body engine. In a way, this gives a bit of an outlook what might happen in other scenarios. So what we're dealing with here now is actually a fairly old paper from SIGGRAPH on cloth simulation by Robert Ritson and colleagues. Here you can see a video which, it's more than 20 years old by now. Back then was not real time. This was rendered. And these are the kinds of simulations that you can get out of the simulator. Nonetheless, I think it's irrelevant. By now, you actually can find similar algorithms in many, or parts of it in real-time engines. And yeah, cloth is actually, for many rigid body simulators, a pretty important component. So this goes into a bit more detail of how to couple rigid body engine with essentially something like a mass spring simulator for cloth. And as you can see, this definitely gives non-trivial scenarios. So here we have some pillars and the sphere moving around and the piece of cloth of colliding and sliding along different parts here. So this leads to a couple of interesting challenges. The basic setup for the cloth is not so complicated. It's actually mostly what we discussed. So we have springs. They have both stretching and bending springs, so basically with one distance, a connection so that we can also account for when a material is actually bent. One important parameter for these cloth simulations is the thickness C here. So even around the main springs, these stretching springs in blue here, we have some thickness C that really is taken into account for many of the following steps to give the material a certain thickness. So in reality, cloth is not infinitely thin. It does make sense. And it's actually also important for stability later on. So it's coincidence here goes through the edge. It's just a parameter. This green one could even be outside. This actually would not really matter. It's really a thickness of the cloth material. Why are cloth simulations so bad? Well, here's a mock-up of what could actually happen. The geometry is thin and it tangles up in a nutshell. So we can actually have folds that basically have multiple layers. So if you look at this blue line, which now is supposed to be a cut through a piece of cloth, it's basically just an S shape, right? It just goes back and forth. But here, in this point, we actually have many that are pretty close together. And now the worst case that basically can happen is that several layers go through each other and we lose track of which side we're on. So what can happen is that this top layer basically goes through both of the other ones, and suddenly now, it's actually difficult to say, well, these collisions are happening. We can easily detect, here's something going through other pieces of cloth, but now it's actually difficult to figure out what is the order here. Which side should we be on? Should we be on the left or right of each of these? Or, you can imagine that many of these inside checks, even if we potentially resolve one collision, maybe we still detect the other one. And then if we try to resolve this one, we go back to the other one. These kinds of tangling situations can be really difficult to figure out. And in the computer, you can't do what we're doing now. You can't just take a step back and cut through and take a look, but we just have a point and some normals and some information about it. And from that, we need to decide which direction to go in. So yeah, situations like these are really, can be really difficult to resolve. And in a way, a lot of effort here is now spent to try and prevent this. So ideally, we actually don't want this to happen, because if we have the state, we're in trouble. So we try to make sure we don't get there. Collision detection is, on first sight, relatively simple. So we have an axis-aligned bounding box hierarchy. So we have triangles for a mass spring system, and then an axis-aligned bounding box, as simple as it gets. But it's actually computed not just for the triangle, but for old and new position, plus the thickness value, the C from before, and another margin. So we basically have a box around, right, 2 time steps. It's a bit illustrated here. So the whole motion across a time step, and then plus these plus 2 safety margins. So the box is actually probably quite a bit larger than individual triangles, to be on the safe side. We ideally don't want to miss something that could happen here. Then what this algorithm actually also does is perform a full continuous collision detection. That's actually something we have not discussed, but this is really looking at, for a triangle and the 3 points over 1 time step, well, with the motions, 2 of them, how and at what time could they collide? Right. It makes the collision detection a bit more costly. We haven't talked about these lower level tests at all, so it goes a bit beyond the scope of the lecture. But one of the unfortunate things is it's a continuous collision detection, so it really takes the motion into account. It still misses things. It still doesn't solve these problems. Then inaccuracies, and then potentially also cases that it really can't easily detect. So there's another safety margin actually here on the sides of the triangle, and also in time, because this continuous collision detection actually really looks at the time step as well. So yeah, one thing to note here, there are really a lot of safety margins. Essentially, every step along the way, we have some buffer. There's epsilon in time and in space for every step along the way to make sure we don't miss anything. You rather spend a bit more effort here than miss a collision and get into these bad states. Yeah, so collision resolution is now actually happening similar to before. But yeah, in line with what we actually discussed, the goal is not to, or what turned out not to be practical, is to guarantee that we resolve everything in one go, but rather as much as possible. So what turned out to be important is to actually have inelastic collisions. So unlike rigid bodies where things bounce back, for cloth, it's typically too bouncy anyway, and the collisions basically should happen inelastically. So we just want to push things out, but not really fly out of each other. Cloth is typically quite soft and does not bounce as much. There is this relaxation constant. I hope you remember from back then. So we actually don't resolve things either in position or velocity all the way, but only with a factor of 0.25. So 1/4 of the update is only applied, meaning we're actually left with 3/4 of the problem, and potentially have to do this many times. But this helps to basically spread things out. So instead of going to one point and fixing it all the way, potentially causing trouble and overshooting, we just do a small step and then do all the other points and then keep on pushing out and out. If we do this often enough, hopefully overall, the global picture, we have something that is resolved. And yeah, then there's actually some special care to be taken for friction effects with cloth, with this thickness of the cloth, so that things stay in contact with respect to their thickness for computing friction forces. But right, this is a bit special for the cloth simulations. And interesting, if you look at the paper fix-up that was necessary despite this already relatively expensive iterative procedure for resolving the collision. The paper proposes they call it rigidification step. So the idea is, if you have some really tangled scenarios like this one, where it's difficult to resolve collisions, basically you detect this after the previous step. If you cycle often enough, right, you hit a threshold, you say, okay, we spent enough resources here, this cannot be easily resolved. Then you check which collisions are remaining that are not fixed. And then it basically detects whole regions. So in this case, kind of tries to cluster regions of problematic points. The orange part here on the green cloth and the other line on the blue cloth. And now it says, okay, now we treat these like rigid bodies. We don't even try to locally resolve this with like a soft cloth, but we just fix it relative to each other and then separate the whole chunks. So in this case, this would give something like the bottom picture. So we just take these orange chunks, treat them as larger blocks, and move them out. The idea is a bit that, yeah, this gives us larger displacements of larger parts a bit more easily, and along the way hopefully resolves many of the smaller scale collisions that happen. This is very unphysical, but was found to be necessary. The paper actually also does more advanced integration, so it does treat the damping and elastic forces of these mass spring systems for the cloth implicitly, like we discussed, with an actual solve of a linear system. It also gives some stability, eventually giving damping from the solver, and it uses for the time stepping, a Hoyne integrator, so second order time step. Also in contrast to rigid body engines. So here, if we now have more complex effects in the mass spring system, it might actually make sense to use a higher order integrator for rigid bodies only. This would not be necessary. Yeah. Also, what the note is, despite using this Hoyne integrator, all these collision, static friction, stacking and friction effects are actually not taken into account with the time integration. Those are, again, if you want, like Euler step, like single processing algorithms for each time step, because those would potentially be tricky to get into a proper second order integration. So this is not done. Yeah, another interesting version is just displaying these cloth pieces. So also the video that I just showed for rendering actually uses a finer resolution of the simulated cloth. So what you saw is actually not what was simulated. And this is a loop subdivision, doesn't matter too much, but some subdivision scheme on the base of the triangles. And interestingly, they found that just subdividing the triangles can lead to intersections. I think I have a piece of cloth here. So if you imagine this is our rough representation of the cloth, and now for rendering, we make this finer. We might end up with something like this one. So if you smooth out this corner here, suddenly it might actually intersect with some other part of your geometry. Even if the simulator was right on the right side, showing it might suddenly give some flickering or weird undesired effects. And now an interesting fix that they propose here is to treat rendering like a time step. So the step going from coarse to fine is actually treated like a simulation time step, where this motion towards a smooth state is treated as a velocity. So from this here right to the left side, this is one time step that's done before rendering. And now they also compute collisions for this time step. So if your cloth would go from non-intersecting coarse to intersecting fine for rendering, this is detected and prevented. And right, then the nice thing about this is that it doesn't influence the simulation at all. It's really only done for rendering and then thrown away independently for each frame. The nice thing is it basically uses the same machinery. So it can actually reuse the same collision handling and data structures and so on that was there for the simulator. You just apply it to this rendering mesh. There's a slight caveat here that things could potentially jitter a bit over frames because it's done independently, but if it's on a small enough scale, this is actually typically still fine. All right, some more examples. So yeah, this is now from the paper as well. Some more examples that they simulated with this algorithm, and yeah, this part, for example, here when the sphere goes back now, here at the bottom, you can imagine this is now getting quite messy. There are quite some parts of the cross that could intersect, and they're not sticking together here, so that seems to be resolved. Yes, there's a question.
It looks really cool. What kind of frame rate are they getting here?
This is not real time. Back then, this was probably taking on the order of minutes per frame. This is far from real time. I would guess that current engines could handle this in real time, but yeah, what you're seeing here is an offline rendering.
It's not using like a graphics coprocessor or anything like that.
This is 20 years old, so definitely not, no. This was all CPU based. And yeah, you could try to extrapolate from what I'm sure there are performance numbers in the paper, but probably doesn't tell you too much about how it would run on a current, on some current hardware with current implementations. But I'm pretty sure by now you could do this in real time. This is actually on a level of complexity that should be possible at the moment. Yeah. Now we come to an interesting example. This is one that's also found in the paper and now is supposed to be a bit of a stress test. And the important thing is it works so far, the cloth disentangles, so it does not get stuck. It's not too impressive if you look at it like this, but yeah, here, I hope you can imagine, this is a tough part, right? So this is where the cloth is twisted up, and it's not even twisting that far. It's like one rotation or so. If you would keep on twisting, the collisions would just stack up more and more and become tighter and tighter, and the forces would get larger and larger in this place of the knot. So potentially your time step would probably go to almost zero. Those would get more and more expensive. And I'm sure if they could have turned more, they probably would have done so. So probably the simulator did actually break down if you turn it more and did get stuck eventually. I'm sure they tried to run this to the limits. So there are actually also interesting follow-up papers that say, oh, now we can do 3 or more, or right, even 10 of these rotations of such a bar, and our cloth does not tangle up. This is 20 years old, so a few years later, people did improve on this, but with the algorithm as presented, right, there are still limits to the amount of collisions and the toughness of these cases that you can handle. If you want to do even more, you probably need even more complicated collision handling and additional steps in your simulator. So this is in a way still, it works here, but this is actually still a tough case for this more complicated algorithm. Yeah, there's a question?
According to this model, it twists and twisting. Would the bar move up eventually?
In this case, actually, it's not two-way coupled. The bar is fixed. This is prescribed. So the bar could not move up, but it would keep on stretching the cloth more and more. You could potentially do this. You could also give the bar some freedom to move and let it be influenced by the forces from the cloth. But in this example, I think this was prescribed. Yeah, so this algorithm, despite its improvements, actually still has plenty of problems. Also, what they reported, what, for example, is problematic is if you have pieces of cloth stuck between geometries, this sounds sounds unrealistic, but this algorithm was actually used by Pixar, for example, tried to use this for movies later on, and in characters. You often have situations like this, like arm joints are a popular destination where things go wrong for human characters. And in practice then, actually they noticed that if you have cloth stuck in between armpits and so on, it would give weird results. Or also just sharp geometries are actually still a problem for this algorithm. Again, needs additional handling. But as an outlook, this is a fairly open-ended topic. You can find many really hairy configurations for simulations. And unfortunately, with these physics simulations, if you just run them long enough or enough cases, at some point you will encounter all of these really nasty cases that you thought would never happen. So in practice, it's actually tricky to make this work without ever breaking down. It's typically restricted to certain parameter or scenario ranges. Yeah, nonetheless, the main idea is a bit to show, based on our standard rigid body algorithm, these are the points that could be improved or changed. Here's one more complicated algorithm. So we had the collision detection step being continuous here, a second order integrator for these parts of the forces, all these additional relaxation and rigidification steps for the for resolving the positions, and then here all these extra margins for collisions. And hopefully it gives you a bit of an outlook of what topics would come up in other scenarios here for other simulation engines. Sorry. So on the slides you can find a bit of a summary also, but what I want to discuss a bit more now is a wrap up of our actual course content. And yeah, basically we had a nice mixture of topics. I hope you agree, at least to some extent. So some interesting numerical algorithms, data structures, some geometric topics, mechanics as a physics motivator, some best practices. So in a way, a big mix. But hopefully this does actually give you some insights about how numerical algorithms can be applied in practical settings, like in this case for real-time games. So yeah, we did try to keep it a bit more practical, so you see where the numerics come into play. You can find many of these topics also in math or more theoretical lectures, but then I also often found it's difficult to see where this would come to use. Here we try to give examples, which reduces the scope of some of the algorithms, but hence this combination. Yeah, thanks also for the feedback. Although we did not get as much as we hoped, nonetheless, thanks to all those who did submit. If you have any ideas about how to encourage people to give more feedback, we'd also be happy for pointers. If you have additional suggestions at this point, also feel free to let us know. There were some topics, right? We know things are definitely not perfect. Some points that were brought up, for example, are the C++ framework of the exercises, having more actual examples for calculation for preparation for the exam, and also the tutorials. There were some comments about how to improve things. So thanks for those. Especially for those three, actually, we are hoping that we can improve things for next year at least. So we will take that seriously and try to improve things. And also, especially for the exercise framework, the first part, it definitely is outdated and worth upgrading and potentially also moving to other operating systems. I think Linux was requested quite a few times, and hopefully also Mac. So if anyone has interest, I think René also mentioned this already, but if anyone is interested, it would be great to have someone who actually has done it, who has experience, who would like to improve this part of it. So, right, if you're interested in doing some work as a Hiwi or so, then please let us know. We'd be happy about some practical help on that front. And this is something for the next semester that we have planned as a to-do item for us. So let me know if you're interested in this. I think there were some comments already. Yeah, the exam, I'm sure, is also an important topic for many of you. The main end-term one is now coming up on February 12th. Retake one just was a question April 4 afterwards, but that is potentially a bit away. It's kind of at our usual slot, I think at 11 for 90 minutes in a nice room called Jürgen Manchot. Seems to be a chemist from TUM room. So basically it's the interims Hörsaal next to chemistry over there. So please don't confuse this with the second room of the old interims room. It's not the one near the computer science, but the one near chemistry. And then another one, Rudolf Mösbauer, also not to be confused with our main hall or so. This one is inside of the physics department. I think it's this round one in the middle, if I remember correctly. So the room assignments will be made available on Moodle, and then we'll have seating plans on the door, so you will be assigned seats. Potentially, usually we have this TUM exam system, just splits by last name into the two rooms, and then depending on the first characters of your last name, you find a list on the door where you can check your seat. Please make sure to look at that and try to go to the right room. There quite a bit of walking apart, at least a few minutes, so it's worth directly going to the correct one. Details of that also will follow. We'll notify you over Moodle and TUM Online once the assignments are up. In terms of content, I hope you already saw the example exams. So we'll give a cheat sheet of the basic equations. It's by now pretty static. I mean, it's not guaranteed to be exactly the same, but most likely it will be very similar to the one you can find in the example exams. What we're really more looking for is to check that you know how to use these equations. So we uploaded 2 examples on Moodle already, and then it basically covers all topics of the lecture. So right, the slides, tutorials, and exercises. The main questions typically are calculating simple examples or some small questions about pseudocode. But yeah, we definitely won't ask you to write long programs, or typically also syntax will not matter. So what I can recommend is to also, if you just specifically want to prepare for the exam, right, we have 90 minutes, and there's only so much that you can ask in 90 minutes. So we also typically try to keep things simple, right? You won't have very involved single calculations. We try to cover all topics, relatively simple problems of the main algorithms, along the lines of what you can find in the sample exams. Right, so also just to make it explicit, so things like these analytical ODE solving examples, just said very briefly, some examples that will definitely not be covered, or you don't need to read or write the Navier-Stokes equations. That is beyond the scope. But for example, this PDE chapter with the different gradient operators, or how to compute a finite difference, that is definitely a topic that could come up Any questions about the content at this point? Right, I can recommend to look at these examples and treat this as a starting point for practicing, and then also it's usually a good exercise to try and think about other or variations of these questions that could come up and try to solve those. That is usually also a good way to prepare. That's coming up in, I think, roughly 3 weeks' time. Before that, we still have the exercise 4 to finish up. And for that, we will have the in-class presentation here in 2 weeks' time on February 5. So we're actually done with the lecture content. Next week on the 29th, there will not be a lecture. So this is in a way the last real lecture, but for all groups that want to finish exercise 4, please make sure that ideally your whole group, or at least a large part of your group, are here to present the exercise. That will be February 5. And then right after the in-class presentation, we're planning to do these oral exams. So that is now scheduled for February 5 and 6. I've mentioned before initially, so this is really just double checking that you also worked on these. Typically, if you really wrote the code, there should be no problem. I can nonetheless recommend that you double check your implementations. We have collected all your submissions. We bring those on a notebook, and then typically we assign 1 slot for each of the groups. So, right, group 23 will get, I don't know, a slot at 10 on February 6th, and then all people from your group who want to get the bonus for the exercises ideally show up for the time slot. We have a small waiting room. You can just wait there, and then we call typically people 1 and 1 from your group. So at some point, right, will be next group 23, and then we get every member of that group in. We typically ask you randomly about one of the questions, specifically about the implementation for one of the first 3 exercises. Right, about some simple data structures or how you did certain parts of it, and let you demo some of the main things, just right to check that you're actually familiar, that you worked on these implementations. That is planned for basically right after the exercise 4 presentation. So exercise 4 is actually not part anymore of these oral exams. So exercise 4 is really handled with this in-class presentation, also because it's so free. This is really more a matter of just checking it off, right? It's usually, we have some groups who do really impressive stuff, but if you don't have the time, if you show some basic coupling of mass spring and rigid body systems, that's also fine. There's typically quite a range of different demos that come out of this assignment. But exercise 4 is done with that. So after our meeting here on February 5, this won't be topic for these oral exams. And for these, by now actually, Felix was just setting this up. It should be active around now, or if not, at least later today. You should be able to sign up for these time slots over Moodle. So we have 1 slot per group, right? If you have multiple people in your group, you don't need to sign up, or not everybody individually needs to sign up. You just need 1 slot per group. And we will group these because attendance of these in the past has varied quite a bit. So we typically do have 2-hour slots, ideally come sometime around the beginning of that. And then we have a waiting room, and then we'll just call in all the groups who actually decided to go for the bonus, and call them in 1 by 1. But yeah, ideally, everyone should show up near the beginning of the time slot, the one that you signed up for this examination. The actual one per person then is usually very fast. It's maybe 5 minutes or so. Yes, there's a question. Yeah. Right. So the question was, to repeat, this is a common topic. If you have members that are not active anymore, there's also no problem. Just sign up, and everybody who wants to get the bonus can come. Also for the presentation on the 5th. This unfortunately is quite quite common. I think many groups by now have reduced from 3 or 4 people to maybe 2 or maybe even 1 person. It's enough if all the people who still want to continue show up. It's no problem if people dropped out. You don't need to notify us, or potentially at that time we will ask, right, whether these other people that were on the list initially will show up, but this is no problem if your group got smaller over time. Yeah. Yeah, no, this really only applies to people who are still active. That is sufficient. Oh yeah, and the Moodle sign up should be up till basically before next Monday. So if you sign up any time during the next week, that is sufficient. Yeah, any other questions about the exercises and or exam topics? If not, then thanks so far. And yeah, if you have any other suggestions about the lecture, right, let us know. Otherwise, hope to see you in 2 weeks for the demos. Thanks so far. Bye, everyone.